Assalamu alaikum dear students, welcome to the lecture of the quantum mechanics. In this lecture we will discuss the solution for the problem number 6.1 and this is chapter 6 of the quantum mechanics by zeittli. The problem says that a spinless particle of mass m is confined to move in the xy plane, meaning our particle is moving in the xy plane under the influence of the harmonic oscillator potential. Definitely particle is moving in the xy plane, so the potential is given, which is v as a function of x and y is equal to m omega square over 2 and 2x square plus y square for all the value of x and y. Then in part A we are being asked to show that the Hamiltonian of this particle can be written as a sum of the two familiar one-dimensional Hamiltonian hx and hy. Then show that h commute with Lz, which is equal to this. The first part, we have to write Hamiltonian as sum of, total Hamiltonian should be equal to hx plus hy, because our particle is under the influence of the potential which depend upon x and y as follows. Okay. The first thing, in order to solve the problem, we start with the definition of one dimension. For example, our one dimensional harmonic Hamiltonian is equal to x is equal to minus h cut square. This is equality sign, minus h cut square, h cut over 2m partial square partial x plus m omega square over 2 and x square. This is Hamiltonian for one dimension, because we have two dimensional potential which is x and y. So for this Hamiltonian will be modified as h will be equal to minus h cut square over 2m. This is minus sign, h cut square 2m partial square partial x plus partial square partial y square plus m omega square over 2 into x square plus y square. Okay, we can write this into like this. If we write it separate, h will be equal to minus h cut square over 2m partial square plus m omega. We have collected the term of x separately and collecting the term similarly for the y separately, which will be equal to plus minus h cut square 2m, and this is Hamiltonian for y and this is Hamiltonian for x. We have separated Hamiltonian of x and y in this step, and then this h is equal to this, and this Hamiltonian for h, which is h is equal to hx plus Hamiltonian for y. Thus we have achieved, let's write the Hamiltonian h is equal to hx plus hy. This was the required solution. In the second part of this statement, we are being asked that we have to show that h commute with the Lz, and we have to find the commutation of h and Lz. Okay, which Lz is equal to this, as you are looking this, we have to put this. So to show the commutation relation, actually we do it explicitly. Let's do it first for hx, and for the symmetry this will give hy, and we will write. So hx is equal to, we know that hx is equal to minus px square over 2m plus m omega square x square over 2. So hx and Lz will be equal to, this is the commutation of hx and Lz will be equal to minus, this is commutation sign, px square over 2m plus m omega square x square, and Lz, we know that Lz is equal to this whole expression. Okay, so this hx and Lz, and then we will take hy and Lz separately. Okay, this is the value of hx, and this, the second term is value for Ly. So when we evaluate this gives the, we know that by visual inspection and following the following rules, xi and xj is equal to 0, we know that, and pi and pj is equal to 0. Similarly, xi and pj is equal to iota h cut and canonical delta ij. We see that the non-trivial term will be those terms which are non-zero for the following commutation, above commutation relation. If we expand this commutation, px square plus 2m, px square over 2m plus m omega square over 2x square and xpy. If we expand this commutation, you know that 1 by 1 term. So this will give that the non-trivial term, mean those terms which are non-zero will be equal to minus px square root 2m plus xpy, and similarly minus px square root 2m and x into py will be equal to iota h cut over m px and py. Similarly, if we write this, this will be equal to minus m omega square x square 2m and minus y px, which will be equal to minus m omega square x square and this. So this will give minus iota h cut m omega square x and y. So for both term we will have, so we obtain, in place of this term we will write iota h cut m, this is written in this, and in the place of this term we will write this term. So hx and lz is equal to this. Okay, I think in this place we have adopted a short ways. You can multiply this. First we have to take the commutation of this with this, and then commutation of this with the second term, and then commutation of this term with this, and then commutation of this term with this. Some term, two term will be go to 0 and the two term will survive, for which I have mentioned the result like this. Similarly, if we write the Hamiltonian commutation of hy and lz, so this will give us again the two term. The first term will become minus iota h cut m over m px py plus iota h cut m omega square xy, which will equal to 0. And so finally one gets h and lz is equal to 0, because we have to write that okay, we are being asked, we go to question. H commute with lz, mean if then finally we will write that H commute with lz, mean we have to show that hx plus hy plus hz and lz, we have to show this commutation equal to 0. Now first we will when we find out hx commutation with lz, then we will find commutation hy with lz, then commutation hz with lz, then finally we will add this result. This will give us equal to 0. Okay, as we have obtained the hy and lz, and similarly in the above expression you are seeing that hx and lz, and similarly we can find that h and lz is equal to 0, means if we evaluate hz and lz, they will just give some result, then we will add hx plus hy plus hz and lz, this will give us 0. Okay, this was our required solutions. In the next part, find the expression for the energy, levels E and X and Ny. We are again given the potential that V of xy is equal to m omega square over 2 x square plus y square, and we have to find the expression for the energy level. Okay, let's go to solution, then we will try to understand it. To find the energy level, we use the fact that energy level of one-dimensional harmonic oscillator is given En is equal to h cut omega into n plus 1 over 2. If we have two dimension, then we will write E and X and Y will be equal to h cut omega and x plus 1 over 2, similarly plus h cut omega into ny plus 1 over 2. For the one dimension we write this, for the two dimensions similarly it will be sum of two x and y. E and x and ny will be equal to h cut omega into nx plus 1 over 2 plus h cut omega into ny. And then we definitely, if we solve this h cut omega plus h cut omega, this constant term can be added, this h cut omega over 2, and similarly h cut omega over 2 will give us 1, and other term h cut omega into nx plus ny will survive. So we will obtain the result E and x and ny will be equal to h cut omega into nx plus ny plus 1. Okay. And then in the part C, then find the energy of the 4 lowest state and their corresponding degeneracies. We have to find the energy of the 4 lowest states and their degeneracy, mean how many times it is going to be repeated. So the lowest term is equal to, you know that we have general energy expression which is equal to h cut omega nx plus ny plus 1. Okay, we write it again. En is equal to h cut omega into nx plus ny plus 1. This is general expression. Now we will put various value of nx and y, and we can obtain the various nx. First nx is equal to 0 and ny is equal to 0. Then this will give us this, the first lowest state, and the second for nx will be equal to 1 and ny will be equal to 0. This is the next state. And similarly, the next highest energy level is 1, which for which nx is equal to 1 and ny is equal to 1. When this we put this is equal to 1 and this is equal to 1 plus 1 2 and this plus 1 3, so this will give 3 h cut. And similarly, when we put 2 nx is equal to 2 and ny is equal to 1, then nx is equal to 1 and y is equal to 2. Similarly, we can put nx is equal to 3 and y is equal to 0, and again similarly. These are the for this result will be equal to 4 h cut omega. These are the 4 lowest energy states, and you can see the degeneracy, that how it is to find the degeneracy as the function of the quantum number. We have general expression degeneracy for degeneracy gn is equal to n plus 1. So we have found that for n is equal to 0, for this, if we have n is equal to 0, so you can put that if n is equal to 0, this g will be equal to 1. If and g is equal to 2, and for g is equal to 1, n is equal to 0, g is equal to 1, then for n is equal to 1, g will be equal to 2. If we put n is equal to 1, the degeneracy will be equal to 2, and for n is equal to 2, this degeneracy will be equal to 3. You know that this for example n is equal to 1, for n is equal to 1, so this is the first energy level, this is the second. These two are degenerate. We have degeneracy is equal to 2, and similarly this is 1, this is 2, this is 3. These 3 states have the same energy, means for this degeneracy is 3. And similarly this is 1, this is 2, this is 3, this is 4, so this is 4th degenerate energy level. These all states have same energy. So for this g is equal to 4, g is equal to 4, and for this g is equal to 3, and similarly for this g is equal to 2, because this and this have same energy levels. Okay, in the part D, find the degeneracy of the nth excited state as a function of the quantum number n. For n excited state as a function of the quantum number n, so that we can write the degeneracy for the any levels. So D part, it will be generalized part. Okay, from this expression you can write from this expression g of n will be equal to n plus 1, g of n will be equal to n plus 1. If we have any value of n, this will give degeneracy for any state, so thus you can find the degeneracy for any order. Okay, so I will stop at this point, and we will discuss the next problem in the next lectures.